Imagine you're walking along a road and notice that the houses are numbered 1, 2, 3, etc., with each house and number getting bigger and bigger. Then it suddenly stops at 8 and skips up to 10, but there are still empty lots. It's possible to have a number 9 house in one of these empty lots. This is what happened with many of the actinide series elements. Scientists had discovered the naturally occurring element uranium, atomic number 92, in 1789. By the year 1900, scientists understood that there was an element for each atomic weight and had developed the periodic table organizing the elements by this characteristic. At this point, thorium, atomic number 90, and uranium, 92, had been discovered, but they were missing atomic number 91. Finally, in 1913, protactinium, atomic number 91, was discovered. Scientists then began to wonder if uranium was truly the largest element, by atomic weight, out there. For the next 30 years, scientists searched for additional elements. Then, in 1940, scientists created the next two elements, neptunium, atomic number 93, and plutonium, atomic number 94. You may have heard about plutonium, since it was used in atomic bombs. There have been 9 more elements created in the actinide series since then, all between 1944 and 1961. Americium, atomic number 95, curium, 96, berkelium, 97, californium, 98, einsteinium, 99, fermium, 100, mendelevium, 101, nobelium, 102, and lawrencium, atomic number 103. The actinide series includes elements with the atomic numbers 89 to 103. It's shown in the bottom row of the periodic table. This row is separated out from the rest of the periodic table because it, along with the lanthanide series, would otherwise make the table very wide. The reason these elements can be broken into a new section is because they are F-block elements. In other words, they use S, P, D, and F orbitals to fill their outer shells. Recall that abbreviated electron configurations use the last noble gas and then indicate the electron configuration of electrons beyond the last noble gas. For the actinide series, the last noble gas was radon, Rn. Actinium, Rn 61 7s2. Thorium, Rn 62 7s2. Protactinium, Rn F52 61 7s2. Uranium, Rn 5f3 61 7s2. Neptunium, Rn 5f4 61 7s2. Plutonium, Rn 5f6 7s2. Americium, Rn 5f7 7s2. Curium, Rn 5f7 61 7s2. Berkelium, Rn 5f9 7s2. Californium, Rn 5f10 7s2. Einsteinium, Rn 5f11 7s2. Fermium, Rn 5f12 7s2. Mendelevium, Rn 5f13 7s2. Nobelium, Rn 5f14 7s2. Lawrencium, Rn 5f14 61 7s2. All of the elements in the actinide series are radioactive. By studying the nature of these elements, scientists have been able to learn about nuclear chemistry and helped us develop nuclear power. The most commonly used element used for nuclear power is uranium. An element's half-life is the time it takes for half of the compound to decay. The half-life of the actinide elements ranges from 58 minutes, nobelium, up to 14 billion years, thorium. Using the half-life of thorium and uranium helps estimate the age of other compounds, like in stars or rocks. This is one of the methods scientists have used to determine the age of the Earth, or how long ago certain dinosaurs lived. Other uses of the actinide elements include the use of americium in smoke detectors. Americium is still very dangerous and highly toxic, but only small amounts are needed in smoke detectors. As the americium decays, it creates a small current. This current can be interrupted by smoke, which allows the alarm to be activated. The actinide series includes 15 elements with the atomic numbers from 89 to 103. Most of these elements do not occur naturally, but have been created by scientists. They are mostly used for their radioactive abilities in creating nuclear power in nuclear bombs and determining the age of compounds using the half-life, the time it takes for half of the compound to decay. The elements in this series are actinium, thorium, protactinium, uranium, neptunium, plutonium, americium, curium, berkelium, californium, einsteinium, fermium, mendelevium, nobelium, lawrencium.